Yes, OK. So, hello everyone. If you don't know me, my name is Julio. In the past, I was working on things like ATF or the QA framework for testing for NetBSD and FreeBSD. I did a lot of work on packet stores as well in the past, but I hadn't used BSDs a lot recently. And today I'm here to talk to you about something of kind of a crazy project that I've been working on for the last few months and how it relates to BSD. Now, the goal of the talk is to show you this little thing I built since last Christmas. It's a little device that runs BASIC. And the goal has been to try to minimize startup time. So you can see here in the video, I plug it in. And hopefully it works. Well, it's a video. It will work. But then you can see here NetBSD's kernel messages. And then soon after, we have the interpreter ready for us to start working. It wasn't as fast as I would like, but it's getting there. So the idea is to talk to you about how this works. Obviously, this is in this conference because the foundation of the project is NetBSD, right? It's based on NetBSD, so that's what I want to talk about. But really, for the presentation, I have like, 45 minutes of things to talk to you about. But in this time, I would like you to think about the various pieces I'm going to explain, because I think the basic portion of this is the least interesting part. And I've been building many different components to make this happen that I think in isolation are interesting on their own. And they could be built to something more interesting and standalone. I don't know what that is yet. I'm starting to think about what could come out of this project that's more interesting than just a basic interpreter. And I'll give you some thoughts at the end. But just keep your mind open as I explain all the little components. So let's start with answering what EndBASIC is. And after that, I'll cover a little bit of how I took NetBSD, made it cross-compile correctly for this platform, and get the whole thing to build. Then I'll tell you a bit more about, in detail, how the system works internally. And then, again, some of these future thoughts. But EndBASIC is a basic interpreter that I started creating myself about 5 years ago now. And the reason was because I was thinking, hey, I have 2 kids, and I would like them to know how to code a little bit more, right? And I had memories of how I learned to code in the past. And then I tried to find some basic interpreters online or Python interpreters. And everything felt complex. Like, for example, this one has a window to write code in, and then another canvas where you can see outputs of what you type. Then you also have another output window that shows other stuff. And as I tried to get well, not anyone, but I tried with my kids, right? And they didn't understand all this weird stuff. Then my wife was also trying to learn to code as a few years ago. And she was incredibly confused by this, right? Trying to learn Python and trying to distinguish between return values of a function and the side effects of a print command. That was, for some reason, very, very hard to understand. And if you look at Python, it doesn't really help. Both things look identical. So I thought, wait, that didn't happen in the past. I don't know. It's a part of the REPL of this interpreter, right? It's just a detail. And to you, it may seem obvious. But I was seeing someone struggle with it, and it seemed interesting. And the other is, when you try to do something a bit more interesting, you end up with stuff like this, right? You have now you have a computer with multiple windows, and they are overlapping. And you have some buttons on the left side. And if you touch things wrong, then you may get in a state that you don't know how to get out of, especially for, again, kids that don't know yet how a computer works. Or then if you get more advanced, you have to run a compiler. And then the compiler produces a file that has a weird name. Why is all this happening? Right? So the idea was, this is too complex. I want something simpler. And again, I want something that's similar to how I learned to code in the 80s, 90s, which is I learned with this computer, the one on the left. It was, you turn it on, you can type code, it does what you said, and if you mess up, you turn it off, you turn it on again, and it's back to where it was. There is nothing to worry about. It just restarts where it was. Then I moved on to MS-DOS. It was a bit more complicated, but still, you could run Quick Basic, and Quick Basic was also very fun to play with because it had better control structures. You could do graphics still. And you could, if you grew up in this time, you would you would have grown with the computers as well, right? You started learning the basics, and then over time something new came out, and you learn about that, and slowly your knowledge grew. Whereas today, if you try to learn something, there's way too many things to know up front. So that's how the project started. I have not gotten my kids to learn to code with this, obviously. But to me, EndBASIC has turned to be kind of, somebody put it, a forever project. It's a nice, fun place where I can come to try new ideas. So, after I wrote it, I started, hey, the kids have an iPad, and this thing should work in an iPad instead of my computer. So let's try to port it to the web. So I had to learn how to do WASM compilation from Rust, and how to integrate it with JavaScript, how to deal with async and all this stuff. So that was the first thing. I also practiced a lot of Rust, because this thing is written in this language, and I didn't have too much practice before. Then I got into cloud services, because somebody suggested, hey, your thing should have cloud file sharing. So why not? I started and I implemented that thing. Then I got into the Raspberry Pi, and it's like, well, I have these pieces of hardware that I want to control. So let's try to understand how GPIO works, how to drive an LCD. So then I got to implement these features in the interpreter as well. And then let's try to use NetBSD again on this hardware for this project I'm going to talk to you about now. So I had to learn about device tree, because some things didn't work, and I had to figure those out. And most recently, I got into 3D printing, so I could actually make these things happen, right? And I had to learn how does this work? How do I design a model? How do I control the printer? So again, it's a fun project for me, and I've been trying many new ideas. Again, I think some of the ideas behind the project are interesting on their own, more than just this retro programming environment. Now, how does this look like? Oh, well, like this. Yes. Well, I think one of the defining features of the interpreter, it's a bit hard to see with the lights, is that there is just one window, and you can have graphics in it, which I think I've tried to find Python and BASIC interpreters online that would let me render graphics, and all of them had what I showed you at the beginning, like 2 different windows. None of them has this overlapping single console that we used to have in the past, and part of this is because this is hard to do. Like if you want to create just a terminal on the browser where you can type things and then render in a canvas separately, that's actually very easy. But if you want to make both work together, it turns out it's not as trivial. So I think this is one of the defining features of the EndBASIC interpreter. And part of why I think it's important is because the abstractions behind this thing have let me port the language to various platforms very easily. So this runs on the browser, but it runs equally on desktop, because I have ports for Windows, macOS, Linux, FreeBSD, whatever it is. And then now more recently, it works directly on the Raspberry Pi, leveraging the hardware directly pretty much. So now, if you want to know how the language looks like, well, if you have not seen BASIC before, there's some examples here, right? It is strongly typed. As you can see at the top, variables can have a type. BASIC didn't have Booleans, but I added them because why not? I don't try to be compatible with any specific BASIC language, as you will see later. But it has that. It has more complex, what do you call it? Conditional structures, like this select case on the left, and that comes from Quick Basic. It has various types of loops, and most recently it has functions and subroutines, and it has recursion and local variables, blah, blah, blah. Now, this may look old because it's basic, but really, there is no need to scream when you write code. I write all keywords in uppercase because it's more stylistic and looks like more old, but you can write in lowercase, and it doesn't look very different from a modern language. It's just control flow and functions, subroutines, and just you do stuff. So what can you do with this? Well, there is a gallery on the website that I put together recently, which has a bunch of the demos I have created over time to demonstrate new features. You can click on them. They will launch in the browser. You can interact with them. You can press escape, and then you will come out to a console where you can look at the code. But the neat thing is that all of these demos are a couple of 100 lines long each. They don't take a lot of code. So if you learn the basics, you can create very visual stuff very quickly, which are going to think, I believed, I didn't prove it though, that with kids, if they can type something and see the result immediately, it's much more easy for them to get rewarded for what they are learning. Whereas If you try to learn Python and do something on the console, it's harder. I think in these days, the star for kids is Scratch from MIT, and that environment for the web is really, really cool because you can do very interesting things with the mouse and very easily. It's really hard to compete with Scratch, and I cannot win that battle. So I'm not trying. And the last thing I want to say about the language is that I've been trying to keep the core as pure as possible, right? So it's Rust, so you have basically two components that are different crates. The core crate provides you the AST parser and the compiler for this language into bytecode and a VM to run the bytecode. The VM bytecode has no possible side effects by default. Like the code cannot escape the VM, not even print. Now, when you think about the language, and if you look at most languages online today, things like print are part of the core language, and they are always there. And if you want to have print, that means you need to connect your language to a console. And that's a side effect, and I didn't want that for the core part of the project. So I put a lot of effort into splitting that out into the standard library crate, which means it is really hard to implement BASIC like this. I didn't realize when I started, because I thought I'm implementing a language parser, I will do an AST. But BASIC was never designed to be parsed into an AST, right? It was not how things worked in the past. So there are many weird things that came out of this, so that it's really hard to be compatible with what it was in the past. And I made it work, but don't expect it to be pure BASIC because it can't be. And that article at the bottom that I wrote kind of shows some of these surprises I found over time when trying to force this language into the AST idea. Now, this will come very handy later because you can use the core crate to implement DSLs for whatever you want. And it is not tiny, but it's a few hundred kilobytes when you compile in release mode. So it's not huge either compared to most things these days. All right, so that's about everything I wanted to tell you about BASIC. Now, we're going to get into taking this language and making it run on a little Raspberry Pi and trying to make it boot as fast as possible, right? So first of all, I had to choose a base OS. As you can imagine, it's not Linux because we're on a BSD conference, right? But I did look at Linux first because it has the best support for the Raspberry Pi. After all, the Raspberry Foundation is what they support. It has the best Rust ecosystem because that's what most developers use in Rust, right? And I found this thing called buildroot, which tries to automate the process of creating a disk image with Linux and a bunch of packages and let you do that, cross-compiling from your machine and stuff like that. Really cool, very complicated. I tried it out. I had no idea what was happening when it was trying to build stuff. Obviously, I could have learned, but I wasn't interested really, so I didn't. But I did actually try to make a package for EndBASIC so I could test it out. I failed. I contacted their mailing list asking for help on why the dependency resolution wasn't working. I didn't get great answers, so I gave up. Again, because I wasn't interested in building this on Linux, just personal choice. So I went back and said, well, let me see FreeBSD, which is what I run these days on my home server. FreeBSD is great. It has very great developer tools. The kernel is very modern. It has many new features. Hardware support for the Pi was pretty good as well. But the cross-compilation story is not great, unfortunately, right? If you try to cross-compile FreeBSD today to a different architecture, you need to do stuff. And the worst thing is that you need root access to the machine, which for me is not something I wanted for software building. I heard yesterday that FreeBSD 15 is going to fix this, which is exciting, but it's not there yet. So I discarded FreeBSD as well, and I went to NetBSD. The main reason is because I know NetBSD, right? I used to work on it many years ago. I know how to change it and do what I needed, so that was really the biggest reason why I went to this platform. But again, cross-building is magic. There is one shell script that you run. You select which platform you want to target, and you get out a disk image from FreeBSD, from Linux, from whatever host machine you have. You can produce this image for NetBSD. It supports non-root builds, so that's also nice, because I didn't want to need root access. And I did have to check if it did work in my Raspberry Pi, which I already had. So I tried it out. It seemed to work. I'm surprised it didn't work very well, as we will see later. But it was good enough to get started. And as I was working on this, I found that the scripts to generate these images for different platforms were very simple to customize. So I could very quickly create a prototype of this idea. So here it is, the first time I booted the thing after taking the NetBSD installation, modifying the existing scripts to inject a binary I built for EndBASIC somehow. I don't remember how I did this. It was put together by hand. You can see the kernel booting, and then it's slow. It will go through user space at some point. There you go. And then it starts X, because again, EndBASIC needs graphics, so it needs something to render graphics on. And then after a while, finally we get to the interpreter. So very cool. I could prove that I could build this, but it was terrible. And again, the whole process on how to put together this first SD card image was very manual. I had to run manual commands. I think I built the binary for EndBASIC natively on the Pi, which took forever, and I had to copy it by hand. But it was a prototype. So then I figured, well, NetBSD is already running on a frame buffer, right? When it starts, and nobody uses like text mode anymore. All consoles are graphics based, and NetBSD is already rendering text on a console. Why can't I render graphics as well directly on the console? Why is it not a thing that's possible anytime today? It turns out it is possible, right? I looked at the WS display manual page, and one of the first things I saw is that there is this ioctl, or ioctl, I don't know how to pronounce it. Ioctl is better? OK. I learned that.
That's what I got corrected to yesterday.
That's why I learned it, yes. So there you go. There is a ioctl that returns you the size of the frame buffer and the offset. So this is saying, please mmap me somewhere and start writing to it. So I did try that, and it worked. I could write a little program. You can see here a VM where I log into NetBSD in the text console. I run a little C program I wrote, and it rendered graphics immediately without X11. You can find everything in that article I wrote at the bottom. So with this, I proved I can do graphics now without X11, and it's fast enough, I think. Then, of course, people came telling me, no, you cannot do this. Don't be crazy. You cannot render graphics in the frame buffer. It's too slow, blah, blah, blah. But I had this computer. Well, not this one. It was very similar. I had the 386 DX40 in the 90s, which had the 1024 by 768 monitor. And this thing played games. And this thing ran Windows 3.11 in graphics mode. And it did fine without graphics acceleration, right? So why can't a Raspberry Pi with 4 cores running thousands times faster do the same thing with the frame buffer? Turns out it can, right? But when people tell you, no, the graphics are too complicated, I don't know. Obviously, it would be nicer if I had graphics acceleration and if I use Wayland or something. But that doesn't exist on NetBSD today for this platform, unfortunately. And yeah, it would be another excursion for another day. OK, so having proven that I could use graphics, then it's like I need to cross-build for ARM. As I said before, NetBSD is great for cross-building the base image itself. But to cross-build packages, that's a different story. And Rust doesn't make it easy because, well, sorry. Rust makes it easy, very easy, if the toolchain you have already has support for cross-compilation. But obviously, for NetBSD, nobody has set that up. So I could not cross-compile NetBSD's ARM binaries from my Linux machine, for example. So I could have gotten into that rat hole trying to figure out how to do cross-compilation with Rust, which would have been very interesting. But I didn't want to poke that yet. So instead, I went to QEMU. And I had to come up with very complicated mechanisms to set up a QEMU VM. There's many flags on the left side. And I had to figure out how to inject source code into the VM and how to extract the outputs from the VM. You could say use a network connection. Sure, yes. But the problem is I'm trying to use the disk image that the NetBSD build produces out of the box. And that thing doesn't have network access by default. So you need first to configure network in some manner. And What I did in the end is like I have a couple of files that I expose as block devices to the VM, one for input, and just a tarball, exposes a raw block device, and another raw block device that will serve as the output. And then from inside the VM, we use tar to write to the block device, and then from outside, we can just unpack the tarball. Now, on the right side, what you have is an expect script, which talks to the VM through the console, the serial console, and just orchestrates the build. It unpacks the source code. It installs the Rust toolchain natively on NetBSD ARM64. And then it does the cargo build, and then just puts the binaries in whatever they need to be. And again, it uses tar to extract them out. Not great, because building EndBASIC on my machine takes about a minute. Building it in this takes almost an hour. So it's annoying to iterate on, but at least I got it to work in a couple of days instead of trying to figure out the cross-compilation story for Rust. Then I mentioned before that NetBSD has these scripts to generate disk images for embedded devices. And those got me pretty far in getting to what I needed, but they are pretty messy, and I wanted to simplify what they were creating for my purposes, and that was already very complicated. So I said, let's rewrite them. It shouldn't be that hard, right? Oh my God. It was a pain to figure out how to recreate an NetBSD disk image with the makefs command and the install boot and disk label and all these things, because I wasn't following the standard disk layout that the NetBSD images have. I was trying to do something slightly different, as I will tell you later. And there are bugs in the tools that cause the bootloader to not find the kernel in some cases. I don't remember exactly what it was, but it was really painful. I remember having to use box to boot NetBSD and then set breakpoints in the bootloader to try to find out what was happening. And in the end, it was just getting the right magic combination of install boot commands and mkfs commands or whatever it was to make this work. But now I have a script, make image, that you can customize very easily. It's much cleaner than what NetBSD has today. And it just unpacks the binaries we built before in the VM, puts them on disk, then creates the actual disk FFS file system, creates another MS-DOS file system for the boot stuff that the Raspberry Pi needs, and then sets up the partitions, installs the bootloader, and it's done. I will get into details on how this works, because creating a disk image with the NetBSD tooling takes seconds. Like, this thing runs like 3 or 4 seconds only due to the nature of how makefs works, and I found it very cool, but I don't have time. So the next thing was, OK, now I have a script to build binaries, and then I have NetBSD's build sh to build a release, and I have, what else? The thing I just showed you to create the disk image. I had to put everything together. So obviously, makefiles are the way to do that, right? So I created a makefile that has a bunch of commands. You do make image, and then you run the whole process to come up with the final image. But then that thing internally is first creating NetBSD tools, which builds the NetBSD toolchain. Does also a NetBSD release to build the actual NetBSD verbatim binaries. And then it does the make binaries, which does the cross compilation. And then it does the make image at the end, which puts everything together. This took also a while to get it to work reliably, but this is the point where I can do make image from a fresh Linux or FreeBSD host, and it does everything for my target device. And I didn't mention this, but you may have seen it kind of like hinted in the previous slides, where I've been targeting only the Raspberry Pi, and I wanted only to support the Raspberry Pi because that's the only thing I had. But again, cross-building for that thing takes an hour, and running the emulator for ARM64 on my machine is very slow. So I got fed up with that process very quickly, and I implemented support for multiple target architectures in my scripts. So now I can target both AMD64 and ARM. And at the bottom here, you can see the machine-specific code on both cases is like very limited. On the left side, I have 400 lines of code for the ARM side of things, more than half of which are just the kernel configuration file, which I will talk about in a minute. And for AMD64, it's like 70 lines of like the specific install boot command that you have to run, or the specific partitioning scheme you have to set up, and things like that. OK, so with all of this, we have now a way to do make image. And we take some pretty much arbitrary Rust code. We package it with NetBSD, and we get a bootable thing. Now, how does that work internally? So the first thing I didn't have to figure out, but I wanted to tweak a little bit, and that's where I got into all these problems with the partitioning scheme, was the disk layout for my final image. One thing I really wanted to support is I wanted to allow you to write the disk image from Windows or Mac OS, and then be able to look at the configuration of that image right from Windows or Mac OS. So I wanted you to be able to access configuration files. And if you ever use the little device to write a program, I wanted you to be able to back it up from a machine that has Windows or Mac OS, because that's what most people would have anyway. So that means I needed a fat partition, not just for booting the Raspberry, but also to store configuration and user files. And then I put it at the beginning of the drive. Then there is the usual NetBSD FFS file system, which is 320 megabytes. That's the smallest I can make it today with the standard NetBSD installation. I would like to make it even smaller, but I haven't gotten there yet. And then there is a bunch of unallocated space. By default, when NetBSD boots the first time, it will try to grow the partition to fit the whole SSD, the SD card. I disable that because I don't need the space. And then the first boot goes faster. You don't have to wait for it to do the resizing. Interesting things here is I had to get disk wedges and names to work for fstab to, like the first two lines in the fstab say nbox/a and nbox/e. That didn't work by default on the ARM platform for whatever reason. I don't remember. But it's some kernel options you can tune. And I had to get the devices mounted by name, so the same image could work on QEMU and on the real hardware. That was an easy way to do it, and it's nicer to use names. Then you can see the boot home mounted on home. So again, I wanted the user data to be stored on the FAT partition, which is by default mounted on boot. But the interpreter is running as non-root. And FAT does not support multiple users. So I had to remap the home directory that was mounted on the FAT partition into a place where the interpreter could write to it. So then there is this umap virtual file system on the NetBSD, which lets you translate. I have this directory, remount it here, and change users and groups in this manner. So you can configure it. And then now I have a writable /home where the interpreter can write things to. And then I also mounted a bunch of things as tempfs so that you can minimize the writes that go into the SD card. Ideally, I would like to get to a point where the SD card is completely read-only, so you cannot mess it up. And so when you disconnect power, you don't lose. You're sure you're not going to get into a bad state. But I haven't gotten there yet. But I think most of the design is already almost there. Then we head to the kernel. For the kernel, I had to do a few things. First, I wanted, again, to minimize startup latency. One of the obvious things I could do was to trim its size. Like the standard generic 64 kernel takes 18 megabytes. And that's visibly slow to load. Part of the reason is that the SD cards I have are old and very slow. So if I bought a new one, which are very cheap, I would fix the problem. But it's waste, right? I redefined the kernel configuration to be as small as possible for my devices. And I got it from 18 megabytes to 6 megabytes. That made a visible difference in boot times. Then I wanted to minimize console noise. So I used the quiet boot or silent boot. There are two things in NetBSD, and they are not the same. So I think silent boot is the one that is the correct name for -Z. I had to come up with a bunch of patches for various devices that don't honor this setting properly, and they still print spam to the console. So at some point, I should upstream this, but I haven't gotten to that yet. And then there were other things. Like I had to modify the GPIO drivers so that they would allow the shell interpreter to configure GPIO pins as non-root, because by default, that's not allowed. So that's just a little setting. I had to patch the security model to allow that. And as well, for SPI, I had to enable SPI in the device T, which I will show you in a second. And also, as an optimization, grow the maximum buffer size that you can use to transfer data. Then for device interfaces, So this shell has to integrate with various APIs that NetBSD offers to talk to the hardware. So that's probably easy enough on Linux because people have done the work. But on NetBSD loves ioctls for controls we learned yesterday. And there were no bindings for Rust. So I had to figure out how to make that work. It wasn't very complicated, but I had to create new wrappers for all the ioctls that talk to DKIO. And that thing is needed to flash drives properly. Because if you do sync, you only flash, I think it's user data but not metadata, or something like that, depending on the file system that implements the sync handler. I'm not very sure about this, but I had to actually call DKIO force flash buffers or something to make sure that everything was flashed to disk. And I see Taylor scratching his head. Maybe we need to talk later. Then, of course, like ioctls for GPIO control, so you can interact with GPIO from the interpreter, from SPI, so you can drive this little LCD I have here on the left side, and obviously the wscons framework, so I could actually render graphics as I showed you before. Then I had to learn about device tree as well, because, well, first, the SPI bus is disabled by default on the Raspberry. I don't know why. So I had to figure out how to enable it with a device tree overlay. And then, so this here is a Pi 02, and that's not supported by default today on NetBSD current. I looked online. Some people had figured out how to make it work by copying the device tree from the Pi 3B and making it work for this board. And mostly it worked, but the Wi-Fi didn't. So I had to figure out I wanted to make the Wi-Fi work. And in the end, I could finally take the Linux 519 device tree files, put them in NetBSD, and that was enough to get that working. Again, I have patches for this that I should upstream, but I haven't gotten to that yet. OK, then we get to the system startup. Now we have the kernel running. Now we need to actually show the shell. And again, the goal is to minimize startup latency. The first thing I tried was I went into etc/rc. I put EndBASIC shell at the very top so that when init run rc, it would start very quickly. And obviously, it was very quick. But that had several problems, like FSCK didn't run yet. And I needed to run it as an unprivileged user and blah, blah, blah. So there were various things to do. And that's how I ended up today after many iterations of this process. So when the system starts, the first thing it runs is the shaper, which shapes the system according to your configuration file. So it looks into the boot partition that you configured from macOS, for example. It reads the config bus file, and we'll see that in a second. And then it modifies etc to make those changes live for the current boot. Then RC spawns the launcher, which is in charge of opening a bunch of privileged devices, dropping privileges, and running the shell. And that takes over the console. And then RC starts the monitor, which is another daemon that stays around to perform like privileged operations on behalf of the shell. And once that is running, we already have the shell running, so you can already interact with it. And then the rest of the system continues to start. You would say, why not stop there? What else do you need from the system? And well, I need network. And that's why the rest of the system continues to boot. I need the network to be up. I need the Wi-Fi to be configured. And yeah, it could be simplified, but that's what it is for now. So let's look into the individual components a little bit to see more or less how they work. So again, the shaper, the whole purpose of this thing is to start, read the configuration file that lives in the boot partition, and modify the system to make those changes take effect. So on the left, you can see an example of the configuration file. It's actually basic, being parsed by the core crate I showed you before, with a pure VM interpreter that doesn't allow escape in any way. There is no commands. This thing cannot even print or anything. The only thing it can do is set some variables. And then the process that's processing the file can read those variables and use the values. So it does that. It reads the configuration file, and then it goes and modifies etc rcconfd for the launcher and for the monitor to set the parameters for those daemons. and it also writes the WPA supplicant configuration file, so the Wi-Fi can start. Now, I said I wanted a read-only file system, but etc is not read-only. So actually, when I prepare the disk image, etc, all these names are actually symlinks that point into var run to files that don't exist yet. And when the system boots, this thing creates those files in var run, which is tempfs, and then they can be used. So I'm not actually writing to disk at all. This took a lot of fiddling, right? But that's why I'm saying this is interesting, is because, yeah, these things are obvious, but they take a lot of iteration to get them to a point where they work as you want. And that's where I think the interesting part of this project is. Then we move into the launcher. And the whole point of the launcher, as I said, is to start the shell, but also to block I/O while the shell starts. Because if I/O continues, you could visibly notice that the shell was starting very slowly as it tries to render to the console. So what the launcher does, very simply, it verifies arguments, it reads configuration from the command line, sets that login, opens the privileged devices that we need, which are the WS display and the keyboard mux, forks itself, and then it does things like increase scheduling priority to later try to prevent scheduling events. It creates a new session. It drops privileges, which again was very, I'll get to that in a second. Enters the home directory, and then it runs the shell. When the shell is running, it will print the banner at the beginning. It will print any errors that the shaper recorded if it found any syntax errors in the configuration file, because you don't want to stop the boot process if there is any mistakes, right? So it saves the errors somewhere else where you can actually fetch them later and read them. It loads the autoexec file in memory, which is used for system initialization. And then it tells the launcher that, hey, I'm done. I'm done with I/O. Go on, and let the system continue starting up. And then the shell will actually execute autoexec.bas if it was present and enter the REPL for you to start typing commands. Yeah, again, dropping privileges, that has caused me a lot of grief in this whole thing, trying to run the shell as non-root. But when I got into this, it's like, well, if I'm going to ship this disk image to anyone that's interested, I don't want them to end with a Raspberry Pi that's part of a botnet. So I really wanted to try to keep things as locked down and as unprivileged as possible. And I think I got there, but it's not simple. And finally, the monitor is, well, as you can imagine, it's a little daemon that starts in the background. And then when the shell needs to do an unprivileged operation, like reboot the machine or power it off, if you want it to do that, then it tries to open a socket to it. It sends a message, and then it just waits for the reply. This communication, works with the Rust serialization and deserialization crate that's very popular. It uses JSON for the messages. It doesn't have to use JSON, but it was the easiest thing to use. But I really didn't want to go into like dbus or gRPC or things like that because they are overkill for what I needed. Right? I just built my own thing, very small. It does the job, done. Now, not everything has been great, right? There are some problems with the use of NetBSD here. As I said, hardware support is OK. I've got, I think, everything I needed to work. The next thing I want to investigate is Bluetooth. But I think it should work, but I haven't tried yet. But using NetBSD took me into routes I didn't expect. Right? I had to figure out all this device tree stuff to get the Wi-Fi to work. The Wi-Fi driver, I think, is not very stable on the Pi Zero, for example, where it works pretty well on the Raspberry 3. Performance of the boot is not enough. That's not a complaint about NetBSD specifically, right? I think FreeBSD would have the same problem, for example. But there is, well, part of it is the RC system, right? It's all shell. And RC will start, and it has to run many individual like shell scripts, all of which read the exact same massive subroutines, right? Which is a very, very big shell script, and that just takes time. So it's very simple to hook into this init system, and I could actually make my daemons run very early in the boot process and stuff, but there is some overhead there that I don't like. Then the other problem I have is so-so support for modules. Like I couldn't take so the Wi-Fi driver in the kernel spends about 2 seconds or 3 seconds just doing something, waiting for the device to come up. And that's a very annoying pause that I would like to remove. Ideally, I would have the Wi-Fi driver be loaded after the shell is already up and running in the background. But unfortunately, this driver is not modular. It's not in a module yet. And I did try to do that, but it was not trivial, so I kind of gave up for now. But just like this driver, there are many more things I would like to take out of the kernel and load them later lazily, and that I haven't been able to yet. Then I said I have to upstream many things, and I haven't really because NetBSD still uses CVS, and that is annoying, to be honest. Some of the changes I had to upstream were relatively simple, and that's OK. But things like updating the DTBs, and that's the thing I have to do now, it's a massive change. I lost practice with CVS because I hadn't touched these for years now, and it's a scary thing to try. And then there is no easy revert. Like if it was Git, I can easily do things on my own, make sure it works, and then Git push. But with CVS, it's like, oh crap, I made the mistake, and then everybody has to suffer after that. There is also nuts. I didn't have to touch nuts, which is the backtracking system, but if you do, it's very old, hasn't changed for years. And then obviously I run into limitations with Rust itself, which you would expect, right? Because NetBSD is not a primary target for this language. The first one was the ioctls, which sure enough, I could write very easily, no problem. But then what I needed to do now was to profile my shell because it's slow. And I wanted the graphics performance to be better, and I can't profile it because the profiling tools don't work. Cross-building, I figured out a way to do cross-building, but to be honest, it's terrible that I have to use a VM for it. I would prefer to have native cross-building, and I don't have it. So that would be nice to fix. And then native development is not working very well either. I would prefer to develop my changes directly on the NetBSD machine I have. But I haven't got an Emacs and Rust analyzer to play well together for some reason, because it works well on FreeBSD. So that I will need to figure out as well. And these are all very interesting problems to try to solve, but my time is very limited, and I have to pick my battles. So for now, I'm just ignoring the problem, continue to develop directly on Linux, and then I copy code to NetBSD when I need to. It's very painful, but I can make progress. OK, so I asked you before to think about things that you could do with this stuff, right? Because I have some ideas, but I would love to hear from you later if you have any interest of different paths the project could take, right? Because one of them is obviously to make it what it is today, but better. Now let's take the original idea of having this learning environment, and let's try to bring it to completion. And things here would be like, let's try to improve performance, because graphics are still not fast enough yet, even though they could be. Or the language, there are some stupid things in the VM bytecode I created that make the execution slower than it should be, but I haven't gotten to those yet. Then I could get into implementing more APIs, like file management, network management, or sprites, because for actual game programming, you need some sort of sprite manipulation, right, to be efficient. I could improve the language to add records, right, so you can have structs, basically. Or I could implement module support, so you can have multiple files contribute to the same program. I could move to a better VM, so you can even replicate things like pick and poke. That it's like a cool gimmick, but there's not very much use for that, so let's ignore it. But it could be done. It would be fun. I could try to target a different VM. Like at some point, I thought, well, instead of having my own bytecode, let's try to compile to WASM, so then when you run this on the browser, you get native performance from the browser. Or maybe RISC-V, or something that's RISC-V, sorry, something like that. Or compile natively to your platform. That could also be done. Maybe somebody asked me recently, like, have you tried to approach any schools or educators to see if they actually would like to do this? It's like, I could. I doubt the answer would be yes. But actually, I learned last week that someone has created a, well, they are teaching game programming, and they are using EndBASIC in one of their first lessons. So maybe it could work for those environments. An alternative path is like, what if there was no BASIC, right? Again, I think BASIC is hurting this project a bit, because when people see the word BASIC, they think, oh, it's an old language, it's legacy. Why would anyone want to learn such an old thing? Well, it doesn't have to be. You could imagine the exact same project I showed you now, but with a different language on top, and that wouldn't be too hard to do. What if it was a Lisp machine? I don't know Lisp much, but people seem to like it, although it's also old, but could be done. What if it was Lua instead of BASIC? That would be more modern. You could actually learn more modern programming concepts like that. Or what if it was a new brand new language with its own name? It wouldn't help much, but at least it wouldn't have the old stigma, right? Because it would be a new thing. So these are all also different paths this project could take to get you something more modern. Or what if the really cool thing behind all of this is the whole automation that lets you take a Rust program or a script, and it doesn't have to be BASIC, it can be any Rust program, make it use some specific APIs for graphics access, and then have it compile for, again, for a packaged disk image that you can deploy to your embedded device or the browser or a desktop application. For this, I've been imagining, it would be nice. I said before that RC is slow to start, and I really thought, well, I could replace init, create my own thing, create something that is fully in Rust to get a full Rust userland, and start with native binaries from the beginning. So the kernel starts a custom init that knows how to start services in parallel and starts the shell and then the network, and that's it. The idea here that I had was I just need to reuse the NetBSD kernel and libc, and pretty much that's it. So if I did that, then I also thought, well, it would be nice. Maybe you don't agree because Bazel is Java, but it has been, I've been a Bazel developer for a while as well, and I use it for work, and I think it's a good build system. It would be nice for me to have a Bazel build for this project, because then I could very easily cross-compile this with huge parallelism and stuff like that on my machine and target other architectures. And it would be nice also to address the problem of the Rust cross-compilation and things like that. When I mentioned Bazel here, it's specifically is because I was watching this project build yesterday on my 72-core host. And you can see that the build gets stuck in many places, waiting for configure to run, or waiting for 2 or 3 files to compile in parallel because the build has not been properly parallelized. And a modern build system kind of gives you that. And as somebody else asked me, is that why don't you target bare metal, right? It's another option. And somebody in Twitter, X, I don't know how you want to call it, has done that. They took EndBASIC and they made it run bare metal on a Raspberry Pi. That's very cool. It's very tempting, because I've always wanted to write an operating system, but it's also not something I want to tackle, because the really hard part about bare metal here is the network, right? Implementing a TCP/IP stack and implementing support for Wi-Fi and things like that would be too much work. So I didn't really consider that. And yeah, do you want any of this to happen? If so, go to that link. You can provide input and see where we could take this. You have more information about the project on the top right website. And those links are about myself, my website, and my blog. And if you are curious, you can come and see how this works. So I have the ones I built. Happy to show them around and make them run. But yeah, that's all I had. Thank you. Now we may have a couple of minutes for questions, not more. There was one here.
Question? I just have a quick question. When will EndBASIC be self-hosting?
Never. Any other questions?
Excuse me, sorry. When you were talking about the VM and having to configure the network, did you? I don't know if you've had reason to encounter something called Cloud Init.
No.
Okay, so Cloud Init is a thing that is an independent project that is designed for cases where you're spinning up a VM in a public cloud or in a hypervisor, and you have to provide some kind of configuration packet. So you design your VM to expect this information to come in, and it can come in via various means. Like if you're on VMware, there's a parameter that can be provided to the VM, and it gets into the machine. If you're on one of the public clouds, there's JSON packages you can drop in and so forth. And so basically, there's a way to give it what you want the machine to do to configure its environment at startup.
I'll take a look. I didn't know about it. Any other questions here?
All right, this is, I'm afraid, more of a comment than a question.
Okay.
But perhaps an answer to a question you had, well, not so much a question, but in any case. First, we're going to move off CVS probably this year. Second, Rust cross-compilation. I have patches to make that happen in package source.
Nice.
I have not tested it on cross-compiling from a Linux system to a NetBSD system, but some of the infrastructure is in place for that to work. And it certainly does work to build both cross-compile Rust itself as a in-package source and build a Rust cross-tool chain that you can use on, say, NetBSD AMD64 to cross-build packages for NetBSD AR64 or RISC-V or whatever.
Cool. I would like to know more about that.
Some of this is posted to Tech Package. It hasn't been merged yet because it needs a little more review, but we can follow up offline.
Yeah, that's a very interesting rat hole for me. I would like to know more. And yeah, cool.
Well, also, until we get rid of CVS, there's also a thing called Git CVS export commit. You might find that handy. That's what I use.
Oh yeah, I've been using the Git clone for everything.
Oh yeah, but so that you can commit to CVS from a Git repository with CVS export commit. And we can talk offline more about that. But you can draft your patches in Git or Mercurial, whatever, and then one command to move it to CVS.
Any other question? There.
Again, more of a comment. When I was doing some early toying with NetBSD on RISC-V, it turns out there's if you go and do your own user space, you can actually embed a root partition into the kernel as a RAM drive, and then you would have that immutable USB disk that you're looking for. So.
Yeah. Could be.
If you go that route.
Yeah, I still need the thing is that people can still save files from the interpreter, right? So they need to be saved somewhere.
Yeah.
But yeah.
But also, right, and where you are right now, it still makes sense to have the full normal root partition in user space.
Yeah, but if I could mount it read-only, it would be good enough, I think. Because then, there's no need for FSCK at the start or anything. Anything else? I guess that's it. You're free for the next one. Thanks.